We consider here a family of functions, again with two parameters, a and b, and this time it's based on an exponential function, e to the minus bx. And again, we can imagine if we change the value of a, we'd get a different graph. If we change the value of b, we would get a different graph. But those graphs will all have something in common, with just some differences due to the particular choice of a and b. In this example, we're actually given a bit of a hint. The statement is that this function, regardless of a and b, so long as they're positive, the claim is that this function will always be increasing and always concave down for all x. Well, let's see if that's true. If it's always increasing, then we should be able to show that g prime of x is always positive. So let's take a look. What does g prime of x look like? Well, g prime of x, this is a multiplying a function. So I'll have a times 0 minus e to the negative bx, and then we differentiate the exponent to get a negative b, and that will turn into be a times b, a to the negative, e to the negative bx. There we go. And then we ask, is that always positive? Well, we were told that a and b are only going to be positive themselves. That's positive and positive. And any exponential, e even to a negative thing, think of 3 to the negative 5, is just a fraction, but it's always a positive fraction. So yes, indeed, g prime of x is positive for all x, and that means g of x is going to be increasing for all of x. Okay. The other fact we were asked to determine whether it's true or not is whether the function is concave down for all x values. And if it's concave down, that means the second derivative would be less than 0. The second derivative would be negative. And so we'll check that. Let's compute the second derivative based on this function. That's our first derivative. The a and the b are multiplying constants. The derivative of an exponential is the same exponential, but with the derivative multiplied out. And we're going to get negative a b squared e to the negative bx. And if we do a quick sign check on that, we always have minus. A we said would be positive, b we said would be positive. If it's squared, it's still positive. And the exponential factor is also going to be positive. So overall, g double prime of x is negative for all x values. Doesn't matter what x I put in here, this term's always positive. So overall it's going to be negative for all x, and that means g of x is concave down for all x. And so every member of this family is going to have that same shape to it. It's going to be increasing and concave down. Let's throw in some extra ingredients that'll give us some more detail. What might g of 0 be? Well, it'll be a times 1 minus e to the minus b times 0. And that means that this is 0, and then we have e to the 0, which is equal to 1. Well, in fact, that means we're going to have a times 0, which will always be 0. So it's nice to note that that's true regardless of the particular a and b values that we pick. No matter what, all the members of this family will have a point x equals 0, y equals 0. They'll all pass through the origin. Next up, let's ask what happens with the limit. The limit as x goes to infinity of a 1 minus e to the minus bx is going to be what? X is getting larger. There's our x. It's going to be multiplied by a negative value because b is positive. And so we remember that e to the minus x heads off towards 0. And so what are we going to be left with? We're going to be left with a times 1 minus 0, or simply a. So this will indicate a horizontal asymptote. Okay, so we know all points, all g of x functions go through 0, 0. all g of x functions have a horizontal asymptote, but the height of the asymptote depends on the value of a. And we also know issues about its increasing and decreasing. So what might these look like? Let's just sketch them for positive x's. That's usually the most interesting part of the function. So we'll draw them through the positive x values, x g of x. And remember we said they were always increasing and always concave down, so it has to be this shape. Concave down couldn't be this way because that would have a decreasing function. So we'd have some kind of exponential like that. Let's say we make that height 1. This would correspond to a equals 1 because we said there would be an asymptote at height 1. G of x in the long run approaches 1. And it's always increasing and concave down, and it goes through the point 0, 0. Let's say if we picked a half here. Now it's hard to say whether it goes first or last. It probably goes first, but we didn't actually analyze that. But we can say the family member with a equals 1/2 will look roughly like that. And if we wanted to go up higher, let's pick a different color for that. We could go up like so, up to 2. That would be a equals 2 with a nice horizontal asymptote at height y equals 2. So all of these functions share commonalities, and they also are distinct in particular ways depending on the choice of a and b.